Welcome back, class. Go ahead and open your books to page 553. We are doing lesson 7.5, similar triangles and indirect measurement. Okay, go ahead and turn to page 553, lesson 7.5. If you need to pause it and get there, do so. Okay, so what we have here is this word indirect measurement. Okay, indirect measurement basically is the opposite of direct measurement, of course. But direct measurement and indirect measurement are both accurate ways of measuring things. Indirect measurement allows us to use properties of similar polygons for distance or lengths that are difficult to measure. I want you to underline difficult to measure directly. So like direct measurement is when you would actually get out like a ruler and measure something and see, oh, it's 10 inches, okay? So direct measurement, examples of those, we're going to put some examples of things here. Direct measurement example is like your arm. You can get like a ruler or a yardstick or something and easily measure your arm. Or like in the Olympic Games, we have like a long jump. Or in track and field, it's track season. You know, we can measure a long jump, how far someone runs. We can measure like the length, of a basketball court. That's an example of direct measurement. There are things we can just actually get something out and measure. Then there's things that are more difficult to measure. And that's where indirect measurement comes in. Like, for example, like the Statue of Liberty. It's super tall. It would be hard to actually, climb up the thing, have someone, hold a tape measure at the top and someone else, parachute down, holding on to the other end of the tape measure and go, okay, it's exactly this many feet. We can use indirect measurement. Another thing would be like the diameter of the moon. We've had a full moon here recently, so like the diameter of the moon. As far as my knowledge goes, I don't believe we have actually sent astronauts up to the moon and had them grab a giant ruler or yardstick or tape measure and actually walk the diameter of the moon to figure it out. However, we've been able to use indirect measurement to find out the diameter of the moon. Now, one of the first people to actually use this indirect measurement is this guy Thales. He was the first Greek mathematician, and he was able to determine the height of the pyramids by examining the shadow made by the sun. So if you look at the picture over here, what this guy basically figured out is he knew how tall he was. And he knew how long his shadow would be. Or basically he held up a stick. He knew how tall the stick was. He knew how long the shadow that was cast by the stick was. That could be measured. And so although he didn't know how high the pyramid was, he could determine how far the pyramid's shadow goes. And once again, one of Miss Neely's things pops up here, so we need to minimize that. Happens at least like once every other lesson. There we go. So basically, if you remember from yesterday, we set two fractions equal to each other. Well, the thing this guy doesn't know is the P, the height of the pyramid. But he would know the stick's height. He would know the stick's shadow. I'll call that the SS. And then he knew the pyramid's shadow. So he knew these three things, so then he could then find the fourth, the actual height of the pyramid. So what appears to be true about the corresponding angles in the two triangles? Well, they're equal. If you look here, this is a 90-degree angle. The pyramid right against the base, you have a 90-degree angle here. Not there, but here. And then that angle appears to match that one. Those angles appear to match up. So we know they're similar, okay, as well. So it says, if the corresponding sides are proportional, what could you conclude about the triangles? They're similar. So we know that they're proportional because the sun is casting an equal shadow on the stick as is the pyramid proportionally, okay? The sun isn't going to, say, okay, you're a person, I'm going to give you a bigger shadow proportionally than the pyramid. the sun just casts a equal shadow across all things, but how long the shadow is determined by the size of the object. But it is a proportional shadow, all right? So let's go ahead and turn the page and look into this indirect measurement a little bit more. Here we have angle, angle. If two angles are the same, that means there's similarity, okay? One proof of similarity is having a triangle that has two equal angles. If two angles are the same, we know the third will also be the same. And if all the angles are the same, we know a shape is similar, okay? And this, you are actually basically starting trigonometry here. This is the basics of trigonometry. So what it basically determines is if this angle here is the same as this angle here, we know these are going to go up proportionally at the same rate. And if this angle here is proportional to this angle there, we know it's going to go up proportionally at the same rate, and these figures are going to be similar. So here's what it asks on example 1. Determine whether the triangles are similar. If so, write a similarity statement. Well, you look at these triangles right here, and you immediately go, okay, angle E is 62, angle A is 62. And then you go, okay, angle C is 70, angle F is 48, and you might immediately go, oh, nope, not similar. You know, one's the same but not the second. Well, not so fast. You don't know what those ones are. What if this angle here matches that 70? Well, then you'll have that one and then those ones being the same, or if this one's 48. So you actually have to find all of the angles of at least one of the triangles in order to know. So I know there's 180 degrees in a triangle. So I'm going to take 180, and then I'm going to subtract my 62, and I'm going to subtract my 48, so minus 62 minus 48, and I'm actually left with 70 degrees for that there. Well, look at that. Those angles now match. So I have a 62 and a 70, and then if two angles are the same, I know the third has to match. So those are similar. So a congruency statement, or sorry, a similarity statement, not congruent, similarity statement would simply be that triangle, that's the symbol for triangle, GEF is similar. Now the similar is just a squiggly line, okay? Congruent was the equal sign with the squiggly on top. That's congruent, but just the squiggly by itself means similar. So that's similar to triangle. Now I said GEF, starting with G 70 degrees, so I have to do the 70 degree first. C. E is the 62, so I have to do the 62. A. Then F is 48, so I have to do the 48. B. So that's how that would be a similarity statement. Now, this example here. This is an interesting shape. I know that both of these are 110, so I have at least one angle the same. Okay? Then I also know, because of this kind of neat little shape, I know that this angle has to be the same as this angle. Okay? Now, I don't know the actual measurement here. I have no math to be able to determine exactly what this is and this is. I don't have enough information. But because of the uniqueness of this shape, because they have two shared lines right here, I know these angles are the same. So I know there's a 110 and a 110, this and this, and even though I don't know all the numbers, I can make a similarity statement saying that H, K, J, triangle, is similar to triangle. Now H was the 110, so I have to do the 110 first. L, K is the same for both of them. It's in the middle, because that's point K for both, or angle K for both. Then J was the one on the edge, M is the one on the edge. So that's making a similarity statement, okay? So once again, if two angles are the same, it means the third angle will be the same, making them similar. And even if you don't know all the angles right away, make sure you find all the angles so you don't actually say it's false when it's not. Now, going back to the pyramid guy at the beginning, it says one type of indirect measurement is shadow reckoning. Underline shadow reckoning. That's basically where you use a shadow of two figures to then figure out the height of a difficult figure, okay? That's called shadow reckoning, where you use the shadow from two different things to help determine a height, okay? So for example here, it says a fire hydrant is 2.5 feet high, casts a shadow of 5 feet. So here we have our little fire hydrant, 2.5 feet high, but its shadow is 5 feet. How tall is the street lamp that casts a 26-foot shadow? So you can't actually go and measure a street lamp. You can't, or you shouldn't at least, climb up a street pole, and drop a tape measure from the top to your friend at the bottom. That's just not safe. But you can use shadow reckoning to determine how tall street lights are. So what you have here is the fire hydrant that's 5 feet tall. Now this is the shadow. This is the shadow, the hydrant shadow that's 5 feet long. So underneath, I don't put the hydrant stuff. I need to put the other shape, just like we did yesterday. So I know 5 feet is the shadow of the hydrant. So underneath goes the shadow of the street lamp right there. Then across from the hydrant, I need the other piece of information from the hydrant, which is its actual height of 2.5 feet. And underneath that, then is h. I'm trying to find how tall the street lamp is. So now, this is very similar to yesterday, where we have two fractions equal to each other and one part missing. So I know through cross multiplication that 26 times 2.5 should equal the 5 times h, right there. So we do 26 times 2.5, get 65, and then we have 5h equals 65, so we divide by 5, you get h equals 13. The street lamp would be 13 feet tall. Okay? Same idea is used here, okay, in this example, where we have a triangle right here and then a second larger triangle. And this is kind of the start of trigonometry, once again. And this is what they used back in the day to actually measure the distance across a lake. They couldn't take a boat out on the lake and make a straight line from one end to the other with some person holding a ginormous tape measure. This is kind of what they had to do, is they tried to make as precise angles as they could, make one triangle, and then continue in the straight line to an edge of the lake, continue in a straight line to the other edge of the lake, and they could approximate pretty closely the distance across an actual lake, since no one could just walk on water and go across it, So you have line AB right here, and that matches AC, okay? So once again, the matching parts of the two different triangles have to match up with one fraction, and then you have BD right there to match up with CE right there. And you fill in the numbers and you're set up with a similar situation where you have two fractions equal to each other, one thing missing. I know that 320 times BD should equal the 482 times 40. I multiply, I get 19,280 equals 320 times D, so I divide by 320. We get this distance, CE, across the lake is 60.25 meters. Okay. Now let's take a look at actually doing some of these. Look at example 1 here. It says, determine whether the triangles are similar. If so, write a similarity statement. So once again, this is kind of a unique looking shape where I know right away W is shared. These two angles are across from each other. I know that this angle is the same as this angle. Okay, so I know they have that the same. Then I know that they have two 55s the same. That right there is enough to say yes, because, and I make my similarity statement of triangle. I'll do XWY is similar, now I have to do the 55 first, to VWU. Because of, you could do AA, angle, just like we had right there. Angle means similarity. Okay. Now let's do shadow reckoning on number 3. So I need to set up my fractions. So it doesn't, right here I realize, okay, what am I trying to find? I'm trying to find the height of a tree. Okay. That would be something that would be normally fairly difficult to find. So I see here the height of the tree is what I need to find. So I'm going to put my H right there, my height of the tree. So underneath then is the height of the dog. The actual height of 0.45 equals, well now tree was on top, so tree's on top here. Now I use the shadow of 2.2. Then I use the shadow of the dog, 0.3. So I know then, using cross multiplication, H times 0.3 will equal 0.45 times 2.2. Then I grab my trusty calculator. So I do 2.2, well, the 0.45 times 2.2, and that gives me 0.99 equals h times 0.3. How do I get rid of multiplying by 0.3? I divide by 0.3. That leaves me h equals, what I do to one side, I have to do to the other. That 0.99 divided by 0.3, 3.3. Now, there's units here, so remember your units are meters right there. And that's how you use shadow reckoning. Very similar to yesterday's lesson. Come tomorrow with any questions you have.